All right, in this section, we're going to look at everybody's favorite topic, which is word problems. We're going to see word problems throughout this course, really throughout all the math courses that you take. I'm sure there'll be lots of word problems. And you know, the more you do word problems, the more you practice sort of translating the problem that's in English into, you know, an equation or what have you, the easier it gets. You kind of get used to the language that's used, because that translation problem really is the hardest part. Once we have an equation, we know how to solve it, right? I mean, all of the problems that we're going to encounter in this section, we can model with linear equations, and we know how to solve linear equations. So you start out by making sure you read the problem carefully, read it more than once. You want to identify unknown quantities. You want to pick one of the quantities, one of the unknown quantities, and assign a variable to it. Usually it'll be whatever we're trying to solve for. And then any other unknown quantities, try to write it in terms of that variable. Our goal is hopefully to get an equation with a single variable, a linear equation with one variable, because we know how to solve those. And once you've done that, write an equation that models that problem. Sometimes it can be helpful to make a sketch. Sometimes not. If you think a sketch will help, then you should do that. When we solve the equation, we want to make sure that we then answer the question, right? So if they're asking you to solve a particular problem, in this case, in example 2.61, this problem talks about acreage of land, right? How much land is purchased at a particular quantity. If we solve this, the answer is not going to be x equals 5. The answer will be so many acres at this cost and so many acres at that cost. So we want to make sure that when we solve the equation, we then answer the question in the context in which it was given. So let's begin. In this first example, they say that we've got 40 acres of land that are purchased for $20,400. Some of the land costs more than the other. Some of the land costs $650 per acre, and the rest costs $450 per acre. So we want to know how many acres were sold at each rate. So there's two things we don't know here, basically, is how many acres were purchased at $650 per acre, and how many acres were purchased at $450 per acre. So there's two things we don't know. I'm going to pick x to represent one of these. I'll say let's let x be the number of acres purchased at $650 per acre. And if x is the number of acres purchased at $650 per acre and there's a total of 40 acres, that means that the number of acres purchased at $450 per acre is 40 minus x. Alright, so now we've got our variable. We have both of our unknowns expressed in terms of x. Now I'm going to write out the equation that models this problem, and I'm going to kind of do an intermediate step and write what I might call like a pseudo equation. I'm going to write it out kind of in English, but this problem is all about the fact that the total cost of this land is $20,400. So what I need is that the money spent on the $650 acres plus the money spent on the $450 acres has to add up to the total spent, the total money spent. So now what I've done is I've kind of broken it down, and I've got, really I just need to come up with what's an expression for this part here, how much was spent on the $650 acres, and how much was spent on the $450 acres, because I know the total is $20,400. Alright, so for the money spent on the $650 acres, I know they were $650 per acre, and there are X acres. So the amount spent on those acres is 650 times X. cost per acre times number of acres. Next, cost per acre times number of acres for this next bit of land is 450 cost per acre times the number of acres, 40 minus x. Now I have an equation with a single variable that models this. It's a linear equation, and we know how to solve those. So let's get started. I'm going to distribute the 450. 450 times 40 is 18,000. We have like terms on the left side. Also, if we're getting all of our x's on the left, they're already on the left, then I'll subtract 18,000 from both sides. $650x minus 450x is 200x. And 20,400 minus 18,000 is 2,400. And we'll divide both sides by 200. And we find that x is 12. Now we're not done. We've solved the equation, but we need to answer the question. We wanted to know how many acres are sold at each rate. So if x is 12, I'm going back up here. X is the number of acres at $650 per acre. So I've got 12 acres at $650 per acre. And 40 minus x is 28. 40 minus 12 is 28 acres at $450 per acre. Okay, let's try another one. There's some problems we run into. I usually call them mixing problems, and this is sort of a classic type of example of a mixing problem. So here we've got 7,600 liters of a gasoline and methanol blend that is 5% methanol. And what we want to do, apparently looks like we want to add methanol. So we're adding like pure methanol to this blend so that we end up with a blend that is 10% methanol. So we want to increase the concentration of methanol. And we want to know how much methanol we need to add in order to make that happen. So I'm going to kind of just draw a little picture to help me kind of understand what's happening in this problem. I'm starting out, I know I've got 7,600 liters, and this is 5% methanol. I'm going to add to that some unknown number of liters, say X liters, of pure methanol, so 100% methanol. And what I want to end up with is 10% methanol. The total volume I end up with depends on how many liters of methanol we added. So the total volume that we end up with is 7,600 plus X liters. So I've got kind of a picture, a concept of what's going on here, and I can use this to make my equation. My equation is going to be about how many liters of pure methanol I've got throughout the whole process. So we start out with 5% of 7,600. That's how many liters of pure methanol that we start with. And then I'm adding to that 100% of this X liters, because that's pure methanol. And I'm going to end up with 7,600 plus X liters, which is 10% methanol. So 10% of 7,600 plus X liters of pure methanol in the end. So now I'm getting closer to like kind of a proper equation, and now I'm just going to get rid of my percentages and write this as numerical expressions and expressions with X. So 5% of 7,600, that is 0.05 times 7,600. 100% of X is X, and then 10%, 0.1 times 7,600 plus X. So this is an equation about the amount of pure methanol throughout the process. All right, 5% of 7,600 380 plus X equals, and 0.1 times 7,600 is 760 plus 0.1X. Alright, so now it's a nice linear equation. We know how to solve these. I'm going to get all my X's on one side. So I'm going to subtract 0.1X, and I'm going to subtract 380 from both sides. On the left side, I've got X minus 0.1X. This is, of course, 1X minus 0.1X, and that'll leave me with 0.9X. On the other side, 760 minus 380 is 380. Now we divide by 0.9. We have 422.2 liters. And I'm going to answer this in context. 422.2 liters of methanol must be added. Okay, we're going to do one more here, and this is a problem that relates distances with rates, speeds and time, and this is another kind of, I guess I would call it like a bread and butter kind of type of application problem that we see in mathematics, and the relationship between distances and rates and times is that distance is equal to rate times time. Now that equation we might use in that form to help us model, and I think we probably will use it in that form. Sometimes you might find it helpful to, rearrange it to solve for rate or time. But in this case we have a plane making a round trip between city A and city B. And it goes from A to B, and it's got a tailwind on that trip. It's averaging 600 miles per hour, and on the way back it's flying into a headwind, so it's a little bit slower. It's going 450 miles per hour. And we know the total flying time for the round trip is 3 hours, and we want to know what is the distance between the two cities. So there's more than one way that we can use this equation, distance equals rate times time, to help us solve this. And I think what I'm going to do when I solve this is just use the fact that this is a distance, this is a round trip distance, so that the distance from city A to city B is equal to the distance from city B to city A. And so each of these is going to be a rate times a time. And setting it up this way, I know the rates, right? They tell me the rates. So my variable is going to be in the time. I know that it's 3 hours for a round trip. So I'm going to let t equal the time to go from city A to city B. And if it's 3 hours round trip, then that means 3 minus t is equal to the time to go from city B to city A. So let's use these expressions with t and plug in the rates we know. The rate from A to B is 600 miles per hour, and that time is t. The rate from B to A is 450 miles per hour, and that time is 3 minus t. Now I've got an equation with one variable, a nice linear equation with one variable. We know how to solve these. And I'm going to start out by distributing the 450 on the other side of the equation. 450 times 3 is 1350 minus 450t. I'm going to add 450t to both sides. And that gives me on the left side 1050t is equal to 1350. And now we can divide. $13.50 divided by 1050 is 1.2857 approximately, and that would be hours. Now we have to be careful because look, the variable that we solved for is the time it takes to get from city A to city B. But what we want to know, what they've asked us is what is the distance between the two cities. So we actually want to find the value of either this side or that side. It should be the same, right? It's a round trip. So the distance between the two cities let's say I'll take the left side, the distance from A to B is 600 times t. So 600 times 1.2857. I get 771.42, and that would be miles. And we have a built-in check, right? I mean, this should be the answer that we're looking for, but we do have a built-in check. I can also find the distance from B to A, right, using this expression here, and it should be the same. We did have to do a little bit of rounding, so I might expect to be off a tiny bit, but they should give us very, very close values. So 450 times 3 minus 1.2857. That's times 450. That's 771.435. Very, very close. So these check out. This isn't the only way we could have set up this equation. As I mentioned in the beginning, I chose to kind of focus on the fact that it's a round trip and these distances should be the same. But I could also have set up this equation so that the distance was the thing that I was solving for. And I could have used the fact that the total time is 3 hours, so that using distance equals rate times time, if I solve this for time, we get time equals distance over rate. And now that the time to go from A to B plus the time to go from B to A has to be a total of 3 hours. And then just use this version of the formula. And, you know, I guess the advantage to setting it up this way, it would be that the variable that we have is the variable that we want to solve for, so we wouldn't need the extra step at the end in order to solve this. But you could try solving it this way. We know these rates, so we could plug those values in, and then you could solve that equation, and you'll find that you get the same distance.